Hi, I'm Matt Noyes,
Joe Rice, Anthony Del Castillo.
and this is Sagnac interferometry. Important concept in this lab is the topic of interference, which is a phenomena in which two optical waves superimpose to form a final wave of greater, lower, or the same amplitude. Interference occurs when two waves are coherent. This resulting interference pattern maps out the difference in phase between the two waves. In order to assure interference, each wave must be of the same polarization to give rise to interference, since two orthogonal polarization states cannot interfere. Another important concept in this lab is the Sagnac effect, which describes the introduction of phase delay between the two legs of the Sagnac interferometer from a change in angular velocity.
Interferometry is worth learning about because it's widely used in science and industry for small measurements of small displacements, refractive index changes, and surface irregularities. Particularly, the Sagnac effect is important to learn about as it plays a huge role in laser gyroscopes, which can be used in a system for measuring or maintaining orientation and angular velocity.
In this lab, there were several key results. The first was that we were able to obtain fringes as expected, as shown here on this screen placed behind our interferometer. After obtaining fringes, we separated the beams in spatially, as they passed through our interferometer and placed a gas cell through one of the path lengths. This altered our OPL, as you can see by the oscilloscope measurement taken right here. This oscilloscope measurement shows the difference between the two path lengths, and it also shows how complementary they are. The complementary nature is shown here by the red line, which is a subtraction of the two. As you can see, it crosses the axis at the points where the two meet.
Overall, this confirmed our prior knowledge of interferometry, as an interferometer light from a single source was split into two beams, and they traveled different optical paths and then combined again to produce an interference pattern. And that interference pattern gave us information about the difference in optical path lengths of the two legs of the interferometer.
One thing I liked about this lab was the pressure vessel section. Seeing the phase delay introduced by a variable index caused by a change in pressure was just a good demo. One part of the lab that I didn't like so much was the single plate quartz crystal with the common path configuration. How much it changed the phase delay between the two legs wasn't really that significant, and it was hard to see on the oscilloscope. We were able to get results, but just not very good ones.